In the previous videos, we have established a few properties of logarithms listed here. In particular, the power rule states that log base a of b to the n equals n times log base a of b. I would like to introduce another property which is similar to the power rule, but takes the base into account, and it's what I'd like to call the extended power rule. The extended power rule is log base a to the m of b to the n is equal to n over m times log base a of b. This property can be proven using the change of base formula, which is another property I will cover in a future video, but you can think of the extended power rule as a more general form of the power rule in practice. The basic idea is that if the base is larger, the entire logarithm is smaller because you only need to raise a larger base to a smaller exponent in order to get the same number. So let's see some examples of when we might want to use this rule. Let's say we have an expression like log base 4 of 128. Both the base and the argument, which is the top part of the logarithm, or the 128 in this case, are quite clearly powers of 2, so it wouldn't be too hard to work out the exact rational value of this logarithm. But we can use the extended power rule to make it a little more clear. So 4 is 2 squared, and 128 is 2 to the power of 7, so we can rewrite the entire logarithm as log base 2 squared of 2 to the power of 7, where m, which is the exponent in the base, is equal to 2, and n, which is the exponent in the argument, is equal to 7. So we can use the extended power rule to rewrite the logarithm as 7 over 2 times log base 2 of 2, and of course, the 7 over 2 comes from the n over m in the right-hand side of the formula, where n equals 7 and m equals 2. Log base 2 of 2 is just equal to 1, so this entire expression simplifies to 7 over 2. So here's another example. Let's say we have log base 2 squared of 2 of 64 square root of 2. Both the base and argument have a radical expression which implies fractional exponents, which are a little harder to work with. So this is where the extended power rule is really helpful. In the base, square root of 2 is the same as 2 to the 1/2, so 2 square root of 2 is the same as 2 to the power of 3 over 2. For the argument, 64 is 2 to the 6, and square root of 2 is 2 to the 1/2. So 64 square root of 2 is the same as 2 raised to the power of 6 plus 1/2, or 6½ by exponent laws, which is equivalent to 13 over 2. So 64 square root of 2 is 2 to the 13 over 2. So we can rewrite the entire logarithm as log base 2 to the 3 over 2 of 2 to the power of 13 over 2. So in this case, n equals 13 over 2 and m equals 3 over 2. So using the extended power rule for logarithms, we can rewrite this as 13 over 2 all divided by 3 over 2 times log base 2 of 2. So to simplify this complex fraction, we need to multiply both the numerator and denominator by 2. So if we do that, then 13 over 2 all divided by 3 over 2 simplifies to 13 over 3. So the entire expression becomes 13 over 3 times log base 2 of 2. And since log base 2 of 2 is equal to 1, the expression simplifies to 13 over 3. So let's say we have something like log base 8 of 81. 8 is clearly a power of 2, and 81 is a power of 3. What if we wanted to rewrite this logarithm in terms of log base 2 of 3? 8 is 2 to the 3, and 81 is 3 to the 4. So we can rewrite the logarithm as log base 2 to the 3 of 3 to the 4. We can use the property to rewrite this as 4 over 3 times log base 2 of 3, and the expression is now in terms of log base 2 of 3. So here's a longer example. Let's say we have log base 4 of 27 divided by log base 8 of 243. We might not know the exact values for both the numerator and the denominator, but if we rewrite both logarithms in terms of log base 2 of 3, we might be able to find an exact value for the entire expression. So 4 is clearly 2 squared, and 27 is 3 cubed, so we can rewrite the numerator as log base 2 squared of 3 cubed. For the denominator, 8 is clearly 2 cubed, and 243 is 3 to the 5. So we can rewrite the logarithm in the denominator as log base 2 to the 3 of 3 to the 5. If we use the property, we can rewrite log base 2 squared of 3 cubed in the numerator as 3 over 2 times log base 2 of 3, And we can also rewrite log base 2 cubed of 3 to the 5 in the denominator as 5 over 3 times log base 2 of 3. The log base 2 of 3 in the numerator cancels out with the log base 2 of 3 in the denominator, so this just becomes 3 over 2 divided by 5 over 3. 3 over 2 divided by 5 over 3 is the same as 3 over 2 times 3 over 5. So whenever we're dividing by a fraction, like 5 over 3, we just have to multiply by the reciprocal. So instead of dividing by 5 over 3, we multiply 3 over 2 by 3 over 5, which is the reciprocal of 5 over 3. If we simplify this, this is just equal to 9 over 10. So the entire expression, log base 4 of 27 divided by log base 8 of 243 is equal to 9 over 10. So here's another example. If we look at all of the bases in the logarithms in this expression, they're all clearly powers of 3. And if we look at all the arguments, they're all clearly powers of 5. So we can use the property to simplify this expression into a nice rational expression. So log base 9 of 125 is the same as log base 3 squared of 5 to the 3, and log base 27 of 25 is equivalent to log base 3 cubed of 5 squared, and in the denominator, log base 9 of 625 is the same as log base 3 squared of 5 to the 4, and log base 3 of 25 is the same as log base 3 of 5 squared. If we use the property, log base 3 squared of 5 cubed is the same as 3 over 2 times log base 3 of 5, and log base 3 cubed of 5 squared is the same as 2 over 3 log base 3 of 5. And in the denominator, log base 3 squared of 5 to the 4 is the same as 4 over 2 log base 3 of 5, and minus log base 3 of 5 squared is the same as minus 2 over 1 times log base 3 of 5. In the numerator, 3 over 2 times log base 3 of 5 plus 2 over 3 times log base 3 of 5 simplifies to 13 over 2 times log base 3 of 5. And in the denominator, 4 over 2 times log base 3 of 5 minus 2 over 1 times log base 3 of 5 is just equal to log base 3 of 5. The log base 3 of 5 in the numerator cancels out with the log base 3 of 5 in the denominator, so this is just equal to 13 over 2.